Hello, my name is Yves Potvin. I'm the director of the Australian Centre for Geomechanics and a professor at the University of Western Australia. And today I would like to talk to you about the high energy absorption mesh, also known as the HEA mesh. This photo here is a typical drive in an Australian underground mine. This shows good ground condition and normal welded mesh surface support commonly used in most mines around the world. The mesh is held against the rock surface by rock bolts, and this type of mesh has a capacity of holding 3 to 4 tons of rock that could potentially break in between the bolts. So it is installed there to hold this loose rock that could happen in between the bolts. When excessive ground deformation and deterioration occur, the weld mesh often fails at the interface with the rock bolts. So you can see here in the picture that the mesh is being cut by the plate as the ground condition deteriorated between the rock bolts. Fiber reinforced shotcrete, also called fibercrete, is used when the ground conditions are not very good and the mesh is no longer adequate. One advantage of fiber reinforced shotcrete is that it provides immediate support and can prevent the gradual degradation of the rock mass, unlike the mesh, which needs the rock to deteriorate and fall apart before it starts acting. The shotcrete is just sticking against the rock mass and prevent it from deteriorating. Different thicknesses can be applied, typically varying from 50 mm to 150 mm and even thicker. The typical 50 mm fiber reinforced shotcrete can also sustain approximately 3 to 5 ton weight, so not that different to the wire mesh, weld mesh that we've seen before. One of the disadvantages of the fibercrete is that when the rock mass deforms under pressure, the shotcrete will crack. When crack open more than say 30 to 50 mm, it becomes not effective and pieces of fibercrete as well as the broken rock behind the fibercrete can fall down and become a safety hazard. To prevent this, when the conditions are extremely difficult and the rock mass is very poor and degrades, the mines combine the fibercrete and overlay it with sheets of weld mesh, as you can see in this picture. So this works well, but this is a costly and slow installation process, as it has to be done in 2 separate steps. This delays the rate of development mining advance, and in the more extreme cases of very poor ground condition and very high pressure, even this type of support becomes damaged and needs repair. A rock burst is somewhat similar to an explosion, and it happens very rapidly and can cause the total destruction of a drive over a fraction of a second. It happens generally in deep mines when ground pressure are very high and the rock mass is stiff and brittle, a bit like glass. So this type of rock mass does not take pressure well, and it just explodes when it's submitted to this high pressure. So rock bursts can also be caused by large seismic events away from the drive, like a mine-induced earthquake. Another type of problem is when the rock mass is very weak and the ground pressure is high. The ground starts to squeeze and the walls tend to close and converge towards each other. Like the rock burst, squeezing ground can destroy mine drives, but this happens over periods of, say, weeks to months. In both cases, rock burst and squeezing ground, it is very often the surface support, in this case shotcrete and mesh, that fails rather than the rock bolts themselves. Rock bursts causes many fatalities in deep underground mines around the world every year, whilst rock bursts and squeezing ground can cause very costly repairs and delays to mining a bit everywhere in the world. This is an example of heavy support used at the Argyle Diamond Mine in Western Australia. As mentioned before, in Australia we tend to overlay fibercrete and mesh to mitigate the consequence of rock burst and squeezing ground. So in this particular case at Argyle, they start with a first pass of shotcrete directly against the rock mass, and they install it immediately after they did the blast, after the excavation. And then they overlay the shotcrete or the fibercrete with a layer of mesh, weld mesh, which is indicated here in orange. And then this mesh is installed using rock bolts, and the rock bolts are installed at the same time as the mesh. And they finally have a second layer of fibercrete that they install on the lower part of the walls. This is in order to protect the mesh from the equipment not ripping the mesh while they drive through these excavations. So this is just an example of a very heavy support system that would be used in an Australian mine. In South African mine, if they expect rock burst or squeezing ground, they would use a technique called cable lacing, and they've used this rock burst for many years. This rock burst mitigation system for many years. The problem with cable lacing is that it requires extensive skill and manual labor to work out how to lace these cables. The work is often performed unprotected with personal position right at the rock face and exposed to the hazard. It is also very slow and delay the development mining advance. Hence, this technique, although very efficient in both mitigating the problem with squeezing ground and rock bursts, it has not been adopted worldwide because of the labor component and the hazard component. Ortlep and Stacy have tested the various ground support technology in the 1990s using a dynamic drop test. The graph shows in this slide here is the results from all these tests. The graph is show in the y-axis the deflection or the deformation from the support system, and on the x-axis it shows the energy that the support system can absorb. Rope lacing, which are mainly shown within this red ellipse here, show that the system using rope lacing can take large deformation and can also absorb large energy. So the results show the superior performance, the top right corner or the red ellipse, from the rope lacing when the rope lacing is used compared to the lower results obtained by the mesh and shotcretes at the lower part of the graph here. These experiments results supplement the many field evidence in South African mines that rope lacing is a superior support system, as it enhances the surface support capacity, which generally is the weakest part of the support system. The HEA Mesh has been designed to provide a similar performance of the South African rope lacing solution, but without the manual labor and the safety and low productivity issues that goes with the South African cable lacing installation. It is a standard sheet of weld-mesh with an attached steel cable pattern over it. It is designed to overlap between neighboring sheets, as you can see in the lower picture here. This is a series of 4 sheets that are installed together, and there's an overlap in between the sheets. And the results is the equivalent to the cable lacing solution. Weld-mesh supported by continuous web of steel cable anchored by the rock bolts are a very strong surface support. It is installed using a jumbo, exactly the same way as a normal sheet of weld-mesh is installed in mines. Some tested were performed at the Caddington mine, and the trial installation showed that this type of mesh could be installed, or the HEA mesh could be installed just as quickly and as efficiently as a normal sheet of mesh. So there's no penalty in terms of time of installation to install this superior surface support system. The HEA mesh has also been tested in a quasi-static, which means a slow loading. As you can see here, the mesh is being loaded by this jack pulling the mesh. So in a quasi-static conditions in the laboratory of the University of Western Australia. The results showed that the mesh is capable of stretching a long way, and it shows here on the graph. This is the load here versus the displacement. So in this case, in this particular test, the mesh is stretched over 700 millimeter before it fails, and it could take a static load of about 14 tons before failure. So a significant improvement in the capacity of the support system. As part of the research and development program of the HEA Mesh at UWA, a rock burst test was simulated using explosive. In this test, the HEA mesh was installed side by side with fibercrete overlaid by mesh, which is the normal heavy support. So you on this side, on the right side, you get the fibercrete and mesh, which is the normal heavy support used in mines, and on this side here, it's a bit hard to see in the photo, you got a pattern of HEA mesh installed. The wall is instrumented with geophones, and this allows to measure the velocity at which the wall moves as a result of the dynamic wave created by the explosion. So behind the wall you got your explosions. On the wall you got geophones mounted a bit everywhere on these walls, and as the explosion is detonated, the wall is moving and vibrates, and this is measured at the velocity, or the speed at which the wall is moving is measured with the geophones. Here you can see the overall test setup. You can note the location of the explosive charge in parallel holes. So you got here you got the drive, and you got the two support system. This is the cable bolt and HEA mesh, sorry, the cone bolts and HEA mesh, and in this case you got cone bolts and you got the fibercrete and mesh, and behind you got the blast holes here which could be detonated. There's a total of 3 blast holes in a vertical line that can be detonated one after each other separately. So we can do 3 tests from this setup. The typical data we obtain from this test is a peak particle velocity, which I will call PPV. And again, this is basically the velocity at which the wall moves as a result of the explosion. So by having several geophones here, we measure this PPV, and then we can contour the PPV results from the blast. And this is an indication of the shock wave that is absorbed by the ground support system. I will also draw your attention on both sides of the wall, on HEA mesh and on the fibercrete side, you got square painted in there. Each of the square are 1 square meter, and that will be useful during the analysis, as I will show in the next slide. So in the ideal case, we would have wished to have obtained a very uniform PPV, so you got the same amount of shock wave that is induced to both walls. But in this particular test, which I'm showing here, you can see that a much higher PPV was experienced on the side of the HEA mesh. This is the nature of the test. It's explosive. It's difficult to really generate a uniform PPV. This shows the results of the blast on the side of the HEA mesh, where the eye of the shotcrete of the shock wave hit. A few points are worth mentioning here. The sheets of mesh remain laced together, so it's simply open just a bit as a single unit, a bit like a door. In doing this, the mesh pulled out many of the rock bolts. See in the red circle here, you get the rock bolts. In this case, the HEA mesh transferred the load to the rock bolts, which were not strong enough to hold the ejecting rock mass. Where the rock bolts held, the HEA mesh held fairly well. So one could interpret this test that perhaps if the rock bolts have been stronger, the HEA mesh would have held together much better. On the fibercrete and mesh side of the wall, 1/3 of the wall was totally destroyed and projected on the other side of the drive. So the intact portion of the shotcrete and mesh wall here has experienced fairly little vibration from the blast, so therefore it has not been affected. But the part that has suffered significant damage is the part that had a shock wave of significant size. Just to interpret these tests the way we do it, if you remember, my square meters painted on the wall here are reproduced, and for each of the square meters we can interpret a peak particle velocity, or velocity at which the wall has moved. So if you take this this square here, we have a peak particle velocity of 0.9 meter per second that has acted there during the test. Now, by estimating the thickness of the rock that has moved as well, we now have a velocity and a thickness which could be translated into a mass moving. Okay, so if you remember your equations from the famous Einstein kinetic energy, so the kinetic energy is equal to the mass times the velocity to the square. So because we got here a thickness, we can calculate the mass, we got a velocity, therefore we can estimate the energy that has experienced this square meters of ground here, which was transmitted to the surface support. So for each of the square on the test walls, on both sides of the walls, we can estimate the energy that has experienced the surface support or the support system. Now also for this square, we can visually assess how much damage the surface support has experienced. And that's what this number here, the SDS equal S2, we got a surface support scale damage, okay, a support damage scale here, which means S0 means that there is 0 damage, and S5 means total destruction. So in this particular test here, there was S2 damage, which is some deterioration, and very slight damage in blue, and the rest was not destructed. This is not the same results as the test I've shown before, it's just an example. So if you go back to the test where we induce a lot of damage to both walls, basically the interpretation we can make from this test is that for an SDS equal 3, so support damage scale of 3, which means that the support will need some form of repair, the HEA mesh has absorbed 9 kilojoule per square meter, whilst the mesh and fibercrete average 5.4 kilojoule per square meter. So the threshold of damage for the HEA mesh is about 40% higher than the one for mesh and fibercrete. So it shows that the HEA mesh can absorb quite a bit more energy before it experienced this threshold of damage. Other observation is the lacing component of the HEA mesh remained fully intact. Okay, so the mesh, all the sheets of mesh remain laced together, and many of the cone bolts pulled out of the walls. So perhaps with better bolts, the HEA mesh would have performed even better. So the conclusion is that HEA mesh significantly outperformed the mesh and fibercrete, which is the strong support we use in Australian mines. The surface support with HEA mesh is no longer the weakest link, and optimizing the rock bolts system for HEA mesh is likely to further increase performance of the overall ground support system. This completes the presentation, and if you have some ground condition where your fibercrete and mesh or your current support system is not performing well, DSI would be ready to supply HEA mesh at any time. And if you like more information about HEA mesh, please do not hesitate to contact DSI, myself, or the Office of Industry and Innovation at the University of Western Australia. DSI is represented worldwide. DSI Australia will be happy to put you in touch with the relevant local contact representative in other parts of the world.